So, welcome back, everyone. Hope you all had a very great lunch. Well, we now continuing with our invited talks. I would now like to request our speaker, Professor Deepak Kumar Goswami, sir, Professor and Dean, Faculty of Interdisciplinary Studies, IIT KGP. I would now like to give a short first. I'll give a short introduction about our speaker, Professor Goswami, and then we'll listen to him and about his research experiences and the work he is conducting in his laboratory. So, Professor Deepak Kumar Goswami is a professor of physics at the Indian Institute of Technology, Kharagpur, India, first IIT. A postdoctoral alumnus of Northwestern University, USA, and the Max Planck Institute, Stuttgart, Germany, he is a globally recognized researcher in organic electronics and flexible healthcare sensors with over 100 publications in journals including Nature Electronics and Advanced Materials and 25,000 plus citations. He is the founder of Senflex Innovations Private Limited, commercializing breakthrough diagnostic devices, and served as the chief investigator of the multiple projects of national importance, such as MITRE, NNEPRA program, Indian Nanoelectronics User Program, Idea to Innovation, NanoShield, etc. Administratively, he has served as the chairperson, School of Nanoscience and Technology, and currently holds the position of Dean, Faculty of Interdisciplinary Studies, IIT Kharagpur. It's our privilege to have Professor Goswami here amongst us. He has taken out time from his busy schedule and his presence among us, and we are very grateful to you, sir. So please, give us- Sure, sir.
Good afternoon to everybody. Before I start, I thank the organizers, particularly Professor Silver Mukherjee and other members in the team. And it's my pleasure to be here and to talk about some of the things that we have been doing for last about a decade. And today, what I will do is that we're talking about some of our recent innovation and for next generation organic electronic devices for IC security to affordable healthcare. So there are a large number of applications. Basically, I'll focus on that. Uh, Due to the interest of time, so I'll not go through the technical details of each one, which are available in the different publications. But if you have questions, then of course I'll be happy to take and try to answer. So let me just start. That what exactly we do is we develop organic field effect transistor, and what you can see in the organic field effect transistor is you have an organic semiconductor layer, you have insulator layers, and then of course metal source and drain. Uh, and there is a current flow through the semiconductor layer, which is can be controlled through gate voltage. That's the typical design of transistor. So what we do is that we exploit this design and functionality to develop some of the sensors, and we make the transistor as a multifunction device. So we can modify any of these layers like semi temperature sensitive material incorporated into the organic platform, organic filament transistor platform, and then we exploit this temperature sensors for different medical device application like monitoring body temperature, sleep apnea, and chronic obstructive pulmonary dysfunction related disease detection and monitoring. That's one of the things. There are several biosensors which I cover some of them, like albumin level detection directly from blood, SARS-CoV-2 detections, COVID detection sensors that we developed in COVID time, and chemical warfare detection, which we did with the metropolitan framework material. Similarly, we have a strain sensor mainly targeted for heart rate, pulse, blood pulse rate monitoring, moisture sensors for wound healing and breathing pattern monitoring, biosynaptic devices, neuromorphic devices. So these are some of the things. And we already have a few three medical devices which validations are actually going on in different hospitals, and some of the things that we are developing. And all the images that you see in the right side of the slides are essentially taken from the system that we have developed, and we do publish a lot of, mainly these publications and patents are associated with the device which I have listed here, other than other articles. So in that, let me start with the first topic that it's essentially the 2D material-based water mounting for hardware security. Here, what we do is that we have siloxane as the 2D material, and as you can see the flex that we synthesize and use this 2D material based devices for synaptic responses, which you see here that I have giving the response of EPSC, so it's excitatory synaptic current, and then there are other parameter like PPM, short-term plasticity, long-term plasticity variations. So these are actually standard characterization of synaptic device. But more importantly, what you see this down the few data that we have that it actually works like a neuromorphic device where you can give like 28, for example, the first example, 28 pulses. If you expose to this device, it achieves some current, and then of course you can make it forget, and then again the same current we achieve, you need only 4 pulses, so that means it remembers. So once you write and then erase it, second time when you write, it doesn't need the same number of pulses. So it's only like 4 pulses, it can get the same information, so it remembers, and you can make it remembering things, can make it forgetting thing as well. So, looking at the material aspect, what we see is that this material siloxane is has absorption is at the UV region, and pentacene is the semiconductor material which has the absorption at the visible range. So we used UV pulse to exploit this response, which are essentially coming from the siloxane to the material, and then what we have developed, as you can see in the right side, uh, we have is like matrix of or neuromorphic transistor, and there we use different UV pulses. What you see here is not able to use my cursor. Oh, okay. So you can see in these three curve. So you see that to achieve a specific excitatory response, you need a very specific number of pulses. And not only the number of pulses, but also the duration of the pulse, separation of the pulse. So these are very critical parameters that one can use to have a particular level of the output response. And this output response, I can fix of my own, and then the number of pulses I can decide that how many pulses I need. So now once this is achieved, then I can have, as you can see, that something like 5 by 4 matrix. We can write something. Some of the transistors can be blocked to write some kind of watermarking pattern, and these patterns are extremely protected because uh, just to read out the pattern, you need a very specific number of UV pulse. And not only the pulse, but its intensity also one of the parameter. Its pulse width is also parameter. And the separation of the pulses are also a parameter which can be modified. Now we think about that once we develop this watermarking pattern on an IC, and so this is a hardware printing on the IC. but the readout pattern is actually with the developer who has a very specific number of pulses, and then their time domain pattern, which are not disclosed. So therefore, this watermarking pattern is totally unclonable because it doesn't come within the IC itself. So it is essentially kind of physically unclonable watermarking, and that can make the uh, watermarking much more protected, which can be used for IC security. The advantage of this, these are all flexible transistor, and you can see that with something like 4 millimeter diameter bending radius, the property doesn't get degraded, and we can actually develop a model also, which can be used to get out and take out this output response from this neuromorphic circuit. So the idea is, so one of the application, as I mentioned, that can be used to protect the ICs, right, for counterfeit and the duplication of the ICs. But the other idea is that we can also, since these are flexible, these chips can be incorporated to any kind of documents, important documents, and there you can fix out this optical readout field, right, number of UV pulses and their time and separation delta T, and then I can have an optical readout to protect that document itself. And this will be much more protective in compared to the existing the protection that I have normally like RFID and tag or stuff. So those are all physically clonable, and one can really break the code. But this will be, since this is a time domain protection, so it will be very difficult to break it. So these are the things that we have proposed, that this chip can be incorporated into the passport. Like passport normally, it is scanned to get the information, but in this particular technology, if we can make use of it, then it's a number of pulse width, which is a very critical parameter that other people may not be able to know. Then we can protect the passport within the ID card, legal deed, academic certificates, bank notes. If this can be embedded, then of course there are a lot more existing problems can be resolved with this technology. So we are working on, so the proof of concept is already demonstrated. Now all we need to actually scale it up and have a little bit higher pixel size of the transistors, get the circuit done, and then demonstrate that this works for protecting any kind of flexible documents, which will be actually very useful in coming years if we can make it. So let us move to next application areas that we have been working on is essentially the healthcare theranostic and diagnostic sensor development. And here we made a lot of contribution. And you can see there are three different decision areas rather that we have made a lot of contribution. One is the sensing related to blood, human blood. Second set of application is essentially like analyzing breathing pattern and breathing profiling. And there we have developed smart spirometer, smart mask, OptiBreath. So these are, I have given the tier level also because these are very mature, particularly the spirometer as Mark 1. So this is essentially 7. So it's a medical validation is going on in 3 different hospitals. So hopefully in a year time it will be coming out to the product. And the another application area is the hardware. So I'll just try to quickly go through and finish it up. Let me start with this COVID detection system that we developed. The principle was very simple, that we have picked up, and this work actually was done during the COVID period of the first lockdown time. So, so we actually, picked up that how we get infected by the virus. So essentially, the molecule which is responsible, which is there in our, everywhere inside the body, like liver, kidney, lung. So that's called angiotensin converting enzyme 2, and this molecule's function is essentially to maintain the blood pressure in our body. But it also happened to connect with the coronavirus is protein, which are basically spike protein. So this spike protein actually gets connected with ACE2, and ACE2 helps us to, those this virus to get inside the cell, where it disintegrate and get affected. So we picked up this ACE2 molecule as the receptor, and then we incorporated this SC2 molecule into our device. And you can see, so this is the device design, and this thin layer is essentially the SC2, which you put inside inside the grain boundary of pantacene. And then it is a two-step process, detection process. So the first step, you see that we had, in fact, the prototype module developed that time. We have, in fact, the mobile app which are connected to the measuring electronics through Bluetooth. And in a mobile app, you can see the response, and it immediately tells whether it is positive or negative. So here are the data that we collected during that time. So we had about 38 patient data that we collected, and what you see is that there is a two-step detection process. So you first put like 10 microliter DI water on the sensor, and then 10 microliter saliva sample taken from your saliva, and then drop it, and then you measure the current and how the current is decaying. So you see that there's a clear distinction between the decay of current for positive sample and negative sample. And if you look at here, the COVID positive and COVID negative, so you can clearly see that this current decay time is actually much faster for the negative, positive sample than the negative sample. And we can actually figure out that very quickly that whether the sample is positive or negative. And you can see here that these red dots are all actually the positive samples, and they are we confirmed all positive. Except some false the negative samples that we would measure. So our sensitivity of the detector sensors actually something like 94%, which is much higher than the existing even available currently in the market, like, which are essentially something like 70 to 85% is the sensitivity. So let us move to the next one. So this is a COVID detection, a COPD detection system, which again we use this ultra fast temperature sensor. So all the specification also are actually given. So what we did with this temperature sensor is that you can see here that when we actually inhale and exhale, when I inhale and exhale, the temperature that we inhale, so that's essentially the temperature in the air. And when we exhale, it's higher temperature because it's coming out of the body. And since our temperature sensors that we have developed is extremely, fast response, which is something like 24 millisecond. And also the sensitivity is very high, 0.001 degree centigrade. So it can easily profile the temperature variation of your breathing pattern. And if you can monitor that, then I can map your breathing pattern when you are breathing normally. And that breathing pattern is essentially connected to how is your lung is functioning. So that's basically testing the lung function test. So that's how we actually developed the system. And then we were actually surprised to see the current status of the COVID, and current status of the COPD in our country, which is essentially something you will see that 55 million people is affected by COPD. And this data is essentially 2016 and 17. This is the government data. And of course, after COVID, this number has been enormously increased, particularly in this area. So what is alarming is you can see that the gold standard detection of this disease is spirometer, and only 10% Indian pulmonologists use this spirometer to detect. So mostly they actually go with the symptoms and then they start treating, and often this patient later become the COPD burden. So it is very important that we can detect and we can find out that the spirometer is there everywhere. The issue with the spirometer is cost, and the second is the analysis of the data. So both the things we handle, and then we developed of our own spirometer, which you can see. Uh, these are a set of the prototype module, and it is essentially connected to uh, Android app. So this is the develop, and this is the Android app. The data actually taken here, and then it goes to AWS cloud server and do the analysis there itself. And after doing the analysis, report is immediately generated and it comes to your own mobile phone. And you can see this is the profile that you see. This is the post email and post Excel profile. This data is uploaded into cloud server, and it get analyzed immediately because we have machine learning algorithm running in the server. And then this device has been tested and validated.
Introducing Simplex D-Smart Spirometer, a handheld medical intervention designed to detect and monitor lung health right from your home. With advanced diagnostics, it can detect chronic obstructive pulmonary disease (COPD), asthma, pulmonary fibrosis, cystic fibrosis, and sarcoidosis, empowering you with early intervention and proactive care. Meet the Simplex Smart Mask, a revolutionary medical intervention that could be a game changer for sleep apnea detection and management. Apart from this, it serves as a breath analyzer and is versatile as a yoga mask, gym mask, and even for defense applications. Simplex Innovation brings cutting-edge respiratory solutions for a healthier tomorrow. Breathe smart, live better.
Technology has been transferred to the startup company which we incubated, and as I mentioned, that its clinical validation is going on. Some regulatory certification we need, and then we can bring it to as a market. Now, if you look at the gold standard, normally not every hospital uses NDT, which is the Swiss-made machine. It's a basically laptop-based desktop. I mean, it's a like tabletop system, but our system is a handheld small machine, and it's very cheap price, about 20,000, which is in fact the gold standard is about 1.5 lakh to 2 lakhs. And this can be carried even by the ASA worker at village to village. They can collect the data, and the data are actually transferred to cloud server, so the doctor can actually get access to this data from anywhere in the world. And you see that the variation, I mean, comparison with the gold standard data with the same patient with our machine is exactly similar. There are not much variation. We get about like 80 to 85 to 90% accuracy with this. So we are still working on that. There are a lot of data that we need, and hopefully very soon we'll have this system as a product in the market. So I'll move to the next system, which is sleep apnea or yoga must be some of the things that you already see. Now, in this case, what we exactly did is that again, since it can monitor your breathing pattern, so while you sleep, typically like those who snore, so their muscle in the pulmonary tract get released during sleeping, and you block your breathing pattern, breathing portion. And then essentially what you do is that you drop some of the pattern. You can see you drop while sleeping when you actually snore. Now this is often for long days, long term, it can develop very serious disease, and which can make a very fatal to the human health. And what we did is that we developed this small mask. You can see here, so you can use this mask and then sleep, and whole night your data can be taken to your cloud, and you see that how many breath you drop for the whole night, how severe it is, and besides that, it also measures the oxygen saturation level. So when you're dropping your breathing, what is the oxygen saturation level falling in your body? So that parameter also parallelly being taken over and analyzed. So that is what exactly it is done. Typically, this kind of test, the gold standard is sonomography, which is actually you go to labs, the sleep lab, and it's very expensive, like almost 20,000 per night. So definitely, the people like us cannot go to sleep lab and test how good you're sleeping. So this small system can actually be used even at the home, and one can detect the complexity. The third example is this is again the protein-based moisture sensors. Again, I'm telling that there are a lot of fundamental studies for each sensors we have done, which are published, which I'm not mentioning here. But what you can see here is that these sensors are extremely sensitive. This humidity sensors, moisture sensor is protein-based, and it can, if you bring your even fingertip close to the sensors, you don't even need to touch it. Monitor your measure the moisture concentration on the fingertip. So that we actually demonstrated. So it's extremely sensitive, and it's ultra flexible. As you can see, it is developed on something like 30 microns deep. So it's very flexible device. And system of actually won as the futuristic medical technology in the nanoelectronics roadshow, I think 2024. So we had a live demonstration in many places, as you can see in the Digital India, Gandhinagar, and many other conferences, medical conferences, international conferences. It went for a live demonstration. Uh, then the next one is the heart health, as I mentioned. Now, what you see here is the typical ECG pattern, which I have shown there. So, what it does is that when actually the valves are opening and closing, so it actually put a pressure on the blood flow. And if you can monitor the flow rate, I mean pressure on the blood flow rate, then you get some kind of pattern here. And this is typically called the ECG, right? And ECG, you know that it's a clinical diagnostic process. You have to go to home clinic and then you measure it. But what exactly the important parameter in this case is that you can see that the P wave, R wave, Q, S, T, Q. So these are some of the parameters that doctors see, and they actually see how far the separation of the peak, intensity of the peak, PQ separation. So this shape analysis is one of the important things that they do to diagnose some of the complexity. What we did is that we developed the sensors which you see here. This is basically silver nanowire based. In the right side, a sensor strip which you can mount on this artery or vein somewhere where the blood flowing, and you see the series of, it continuously monitor the pattern of your blood flow pulse, and which are shown here. You can show that it can show here, and it can actually monitor your P wave, S wave, and T wave, which are actually essentially also measured in ECG. Now, all you need to do is that you analyze this shape, and then there are many critical diseases that can be monitored. As I listed here, you see the standard pulses, blood pulses, normal, small, weak, large, weak pulses. So these are some of the steps that indicates the complexity in your lung, how this actually functioning in your heart, how they are functioning. And based on this, there are many complexity which are identified. You see, uh, just from the shape. So if you can do this test early and then identify the complexity, then of course there are many diseases can be early diagnosed. So, and this again, it's a very small sensor, and all the technology that we are developing are affordable. It's very cheap. It's mobile app related cheap. Everybody can use this mobile and use this system at home. The last one, I'll stop with this. The last one is the albumin detection system. It's exactly similar way that we developed the COVID detection system, And what we did is, in this case, we used a pentapeptide, which you can show here. And so this is a sensitive, selective to bind with the albumin molecule in the blood. And then we did develop the sensor. And what we found is that it's about accuracies of the order of 4%. So we did have, we did compare with the pathological data and with our sensors. You can see that pathological data like 4.1 gram per deciliter. The same blood from our sensor, we got something like 4.4 gram per deciliter. It's very close. These are our statistical data. So we have taken many samples. And good thing about this sensor is that it can actually measure from millimole to picomole. So there's a range of measurement is very high. So these are some of the sensors and devices that we have been working for a long time and trying to push it to convert into a technology. And I hope that you get some glimpse of the work that we have been. So in that, I thank you all. And these are my team and funding agency. And thank you all for your guidance.
Sir, for such a fascinating talk. So now the participants and attendees can ask their queries to our esteemed speaker. Anyone? I have a question.
Sure.
So, like in the moisture sensor and temperature-based sensor, you have used polymers and proteins.
In the moisture sensor, we have polymers, we is putting the sensor. And the temperature sensor is essentially very important in logistics.
But by using a protein-based sensor, how do you look over the stability of the protein, like protein gets degraded over time in the environment?
Yes, that's a good question. So protein. So these proteins that we have used is most abundant protein, gelatin. So it is there in the market everywhere. Like it stays for not of course its lifetime is not years. Uh, but this since the sensors the plan is like since the sensor is very cheap, right? Material is also cheap. It will be like even through sensors. So uh, mount it, you use it, and then it will later it will change the moment it will.
What about like for
Yes.
take months? So
It will take months. So the way what we have handled in this particular project is that the system that we have developed, so we have in fact a online portal developed. So each prototype has a MAC ID, and then we from the server we actually follow the performance of that device. If moment we see that the current is degrading, we ask them to change the sensor. So we provide the sensor. Sensor are actually sealed inside the vacuum when you develop it, and then when you start using it, maybe you use for 7 days and cheap. And these are very cheap, as you know, the material cost is very low, and you can develop very fast.
thank you so much, sir.
Thank you.
Sir, I have more doubts which I'll communicate
Sure.
in the dinner time.
Sure.
Yes. Now, sir, now I would like to request Dr. Rohit Singh and Dr. Sushil Kumar Pandey to present a memento to our esteemed speaker as a token of appreciation. Thank you, Professor Pandey. Thank you, Dr. Singh.
Thank you.
Thank you, sir. So we are grateful for the time and efforts you took to share your expertise with our IEEE community. We look forward to more such sessions. Moving forward, we have our next invited talk from Dr. Mangal Pandey. It's my privilege to give a short description about Dr. Mangal Pandey. Sorry, Dr. Mangalas, I'm extremely sorry. Dr. Mangalas is a highly accomplished academic and researcher currently serving as an assistant professor at Gautam Buddha University, a position he has held since November 2024. He holds a PhD in the Electrical Engineering Department from the Indian Institute of Technology Indore in the batch of 2020 and is further enhancing his expertise with a postgraduate diploma in data science from IIT Delhi. His professional journey includes significant teaching and research roles at prestigious institutions such as the Vellore Institute of Technology, Chennai, Manipal University, Jaipur, and IIT Bombay as a senior research fellow. Dr. Das specializes in VLSI systems, memoristic devices, and underwater robotics, contributing extensively to this field through numerous peer-reviewed publications in high-impact journals like IEEE Transactions on Nanotechnology and ACS Applied Electronic Material. He is also a prolific inventor with several granted and published patents, including a silicon-compatible Yttria-based memoristic crossbar array and innovative systems for underwater inspection and communication. His work has been recognized with multiple honors such as the first prize at the Marine Robotics School 2023 and the prestigious Vishweshwaraya PhD Fellowship Program from the Government of India. We are very much grateful to Dr. Das for having him here with us to share his information. Sarjit mic दे दो सबको.
So good afternoon, everyone. इसके थ्रू चेंज करना है अच्छा So good afternoon, everyone. My talk is mostly related to future of drone warfare and technical and technological innovations related in the modern conflict. So first I would discuss the outline. I will first show you my work related to underwater drones and then unmanned aerial vehicles, types of UAV, dynamics and flying mechanism, then drone swarms, and the formation control problems components, then the drone swarm and modern component. It is drone kill chain and drone detection and drone kill itself. Now this is my project which I have done with the sponsorship of IIT Guwahati Technology Innovation and Development Foundation, in which we have developed a micro inspection ROV. This ROV is somewhere weight around 10 kg payload with 30 meters depth and should be handled by one man alone. And the design of ROV platform, design of human machine interface, design of storage and packing. So this is the images of product Vesna done today where we did real time testing of our product. So let me show you the first video of our
Sir, you don't want to.
प्रेजेंटेशन चल के प्रेजेंटेशन बड़ा प्रेजेंटेशन
हाँ प्ले करो उसको
साउंड कर क्या बोल रहा हूँ
अपने
ओके सर
Sir, you don't want to take it. Just roll.
It's on just and you would want to see what is happening here. Camera, no? Live. When it detects something.
Right by other direction. Yeah, I'm just driving.
and this is the original testing which we have done in C. So everything is tested. Now we will move to the main content of our slide. This was my work related to unmanned aerial vehicle. So how it is defined and how you define an unmanned aerial vehicle? It has to be a powered vehicle that should not carry a human operator on its own. Vehicle should not have it. Either you can remote control it remotely or it should fly autonomously. Now, this particular grouping of UAVs has been done by the US National Defense Department. Now, types of UAV is basically fixed wing. You can have fixed wing hybrid UAVs, then single rotor or multi rotor. Now, fixed wing UAVs have very long endurance and fast flight speed. And fixed wing hybrid UAVs are generally very good with VTOL and long endurance flights. Single rotor UAVs have very long endurance, but multi-rotor UAVs are easier to design and have shorter endurance because endurance means how much time you can fly with single battery charge. That is how you define it. Now, fixed wing UAVs are generally designed for aerial mapping and the inspection of pipelines or power lines. Although they are relatively more, they need more space to launch. Recovery is problematic with them. These types are not drones is not suitable for VTOL or hover applications. Basically, fixed wing UAV you have seen the Rustam UAV of DRDO. This is a fixed wing UAV. Fixed wing hybrid designs UAV basically are in development. Where what we do, we have a fixed wing as well as some rotors attached to it. These UAVs are still not good in terms of these are still in terms of experimentation stages. So these UAVs are pretty notorious still date in terms of endurance. They have very bad. Now still people want to design them. The reason is it gives you independence in terms of VTOL and as well as you can launch from where you can launch them, especially militaries or defense. People are too much interested in hybrid UAVs because it gives you the flexibility. Now, what are the mechanism? Basically, dynamic and flying mechanism. Yaw movement is basically to control to ensure the stability in terms of z-axis. Pitch movement we use for y-axis control, and rope movement we use for the stability in terms of x-axis. So there are two types of design which you will see generally in quadcopters. One is plus design, which we see plus sign. You can see it first on the left hand side. On the right hand side, you can see an X design. So why you prefer this X design? It is a more stable structure, and but sometimes you prefer plus design. Why configuration? Because it provides you easy maneuvering. So X design is basically is used for if you want to do an aerial survey, because the rotors are basically outside of the screen of the camera viewpoint. Now, all these drones will have something called electronic speed control system, which will use a PWM signal and a three-phase inverter, which will be connected to a brushless DC motor, and you will have a feedback, which will be taking the feedback from this position feedback from this brushless DC motor and giving it back again to the signal processing or control logic, and then it will again feed it to the three-phase inverter. Now, the important thing is to understand why we need these kind of logics. It doesn't matter whether you buy from the same company or from the same lot. Every manufactured product will have some type of variation, because you cannot say that if I make suppose 10 motors in a factory, even with highest grade of accuracy or production parameters, you cannot say that the speed of motor will always be 500 rpm. In real world, when you employ that motor, you may have 501 or 502 rpm and some with 499 rpm. So what will happen that this slight change will basically over the time will accumulate, and this will create a drift in your system. So that drift has to be compensated with the help of this feedback control system, and that is a very important drift. So after that, we generally have something called IMUs in our drones. Most famous drones are quadcopters. That's why we are taking the example of those quadcopters. Now, IMUs will have generally two things. There are multiple types of IMUs. I'm talking about general IMUs. Accelerometer and gyroscope. Accelerometers basically measures the acceleration forces. Gyrometers basically give you angular rotation, and then again you take these two particular parameters, generally minimum these two parameters in a drone as an input, and then this will go to the signal processing and the controller and the state estimation, and basically provide a stable flight. Now the control mechanisms which are preferred in the drones nowadays is PD, PID systems. But when you go through the testing of or you read the literature regarding the PD and PID control mechanism, you will see that they do not have speed of response is not that good with P or PI system. And in control mechanism, you have non-linear or sliding mode controllers. Then you have optimal category of control mechanism where you can have a linear quadratic regulators, adaptive control, and sensor fusions. Now, this is the main problem which we will discuss, that when you employ the drone swarm, why we need to employ the drone swarm? Because single drone, especially in terms of conflict nowadays, you will see, you want to overcome enemy defenses. Drones are pretty much area of interest for defense people. So they want to overcome the enemy defenses. So what they will do, they will mix and match different types of drones. And the problem is nowadays these drones have become so small, so tiny that it is literally impossible to detect on even very advanced radars. So because the radars nowadays are designed, current radars, generation of radars are not designed to detect drones. They are designed to detect very high speed planes, jet planes. So they are, you have right now seen in the US and Iran conflict that US have severely, that the destruction of US radar becomes very easy with a very simple drone. And and the drones are not even technologically very sophisticated. That is the main tactical and technological use of the drone, which we generally tend to ignore. That it is not the technology always, it is how you use it. Sometimes simple things are much more easier to, basically much more easier prone to damage. Now, why we prefer drones? Uh, Now, when you talk about form of drones, you will have something called formations. Basically, formations is basically how a group of drones will fly. So, suppose you want to create a grid formation. You have seen, I don't know, people have seen you can see the drone shows which they will create a phase or something like this. So, that is what we call this is what we call drone formation. So you have huge amount of drones and you want to create some geometry out of it in a 3D space. So what are the components which you should be looking when you are creating a formation or a geometry out of these multiple drones? So what we will see is basically formation representation, the geometrical arrangement, then trajectory tagging, formation generation, formation keeping, then formation switching, collision avoidance. So when you switch the formation, the drone itself should not collide with other drones. It is not pretty easy. The problem is with drones, they have become so small that you cannot put a whole lot of computational power on drone itself. And then obstacle avoidance and formal dissolution. Now, with formation control schemes, we have three types of schemes: centralized, decentralized, and distributed. So, centralized schemes are basically you have one brain which is controlling many smaller units, and this brain, every smaller unit is only talking to that particular brain or that particular what you call hub. In decentralized scheme, what happens? These smaller nodes or drones in our case will be totally independent to each other but will work on the basis of local environmental sensing. So each drone will sense the environment in its vicinity and then take the action in order to maintain the formation. In distributed setting, what will happen? that each drone will communicate with each other, which is seen here, U1, U2, U3, and then they will give information to each other and then try to maintain the formation. So although first one is much more simpler to deal with, but if you move to this hierarchy, you will see the complexity goes up and the communication complexity also goes up. Complexity in terms of maintaining the formation, but each drone when you're talking to, suppose if you scale this problem to 50 drones, then you realize how difficult it becomes. Because then distributed system, each drone has to talk to each other, that much of bandwidth should be available. Especially this becomes a huge problem in underwater drones. So I got two projects just to solve this for even three drones. Underwater drones, it's a huge problem because what the bandwidth which you will get in terms of kbps, you cannot send every information whatever you want. This will be literally impossible. So conventional formation control methods, lead follower, I mean, try to finish it. Leader follower, virtual structure, behavioral based, consensus based, and artificial potential. These are some standard things which we follow. AI based formation. Now major challenges. Now this is what I want to show you. The drone swords in modern conflict. There is no single way to counter one sword. Now, what should we do? We should use multiple detection sensors. Tactical innovations. One example I will give you is a very old method of detection using sound. So, if you read literature, people have basically said it is an outdated phenomena. This will not be used. But with current scenario, we were forced to use it. The drone size becomes so small that the only way to detect is sound. You cannot detect it on radar because it is this is small. So at least you will get some kind of information with sound. So sometimes even outdated scenarios or outdated so-called outdated research which we have left is the only way to escape. And this is right now implemented in Ukraine and Russia war. It is not something which I am talking about that it is research. They are forced to implement it. So this is what we call tactical innovation. Sometimes you are forced to implement something which is what we call outdated scenario. So multiple types of drones. Now, what are the multiple types of drones? One swarm will also have missiles, micro missiles, drones with optical fiber cable, and these cables are very long. Nowadays, you have drones which have 40 kilometers of optical fiber cable. So you literally use those kind of drones. They have their own problem. That is a different scenario. But again, because of going on war, there are so much old innovations coming back that the strategies forced us to use those old innovations. Something what is most important, why these strategies are important, something called drone kill chain. So you have to detect a drone, locate it, then track it, identify it. Sometimes identification is not possible because drone is very small, so what you will identify into it, and then decide it. Not taking the decision whether you have to kill a drone or not depends on even not only on technological solution but something called human intervention in a tactical level. One example I will give, then you have to defeat that hostile drone and assess whether it happened or not. That in reality you have defeated the drone or you have countered the drone or not. So what this and it has to be happen in it has to happen in some seconds. Now you can understand the difficulty of control algorithms. You cannot put all the things which I have written here and say I will put AI and every great algorithm there and it will work. It is not going to work. But in real sense, you do not have that much of computational power, and you will never have that. So what we do, we deploy multiple sensors because some sensors, all sensors will have some problems. They sometimes they will work in certain domain for certain type of drones, sometimes they don't. And then you will have the layer defense systems. Now these are the detection methods: early warning radars, fire control radars, acoustic radars, where I'm most interested and working right now. Radio frequency and the optical detection systems. Radio frequency systems, what you will do? you will simply try to detect the change in the radio noise, the radio uh, signals which are present in the background, the noise of the radio frequencies. Now, this kind of systems sometimes doesn't work. You will see the weaknesses. And in kill chain, you will have two types of problems. Whether you want to really destroy a drone or not, because destroying a drone is not easy and sometimes it is not even economical. You can have very good technical innovations, but it is useless in terms of cost. And then sometimes you disrupt. Disrupt means basically you create a scenario where drone should not able to complete complete its mission. So there are different ways to do it. So here I will stop my presentation. If there is any question regarding it, yeah.
Attendees and participants can ask their queries to our speaker. Anyone?
So since we know that I'm doing that, that say what yes, said what so similar to drone like something that beside water, beside water. I have shown in one drone. So that's what we said. Yes, the drone which I have shown you is the underwater drone. A real one. Like the drone we understand that it is what like, the difference is see the drones which physics the equations does not differ because there is one way to look at it. The equations of air and water mostly are same. The reason is you can also treat water as a very dense air if you want to have very simplified equation. So technically equations. Yes, sir. These things will come, but you can think that it is a highly viscous and highly dense liquid. So say the air does not have that viscosity. Now the problem which you will have and especially face in underwater drone that EMF signals doesn't work. Electromagnetic signals don't work. So you don't have GPS. And once you don't have GPS, and this is the very famous method nowadays. In GPS, you give 0, comma 0. When you get a robot and you get the 0, comma 0 and any equation from that XYZ coordinate, you get a frame out of it. But underwater drones, you don't have 0, comma 0 because there, how will you basically calculate it? There is no way to detect, use any GPS. There are underwater GPS, but those are very complicated solutions. People don't, you can't use it in what you call low cost drones. So the way to do it, there are different ways to do it. Suppose what we did, that we sent GPS coordinate to the drones through our LAN cable. In our project, what we did, we sent the GPS coordinate to the drone through the LAN cable. But there is some restriction on it that if LAN cable becomes too large, and if you are using IME, because of integration, you will have error. So there are some issues depending on the scenarios which you are using.
Thank you, sir. Thank you, sir, for such a session. Now I would now I would like to request Professor Sudeshna Chattopadhyay to present a memento as a token of appreciation and gratitude to our esteemed speaker. Thank you, Dr. Das. We are grateful for the time and efforts you took to share your expertise with our IEEE community. Moving on to our next invited session by Dr. Ankesh Jain, Associate Professor, IIT Delhi. Now I would like to give a short introduction about our speaker, Dr. Ankesh Jain. Ankesh Jain is an Associate Professor in the Electrical Engineering Department at Indian Institute of Technology, Delhi, India. He did his BTech from NIT Allahabad, India, and PhD from IIT Madras, India. He has worked in Freescale Semiconductor, Noida, India from 2007 to 2009, where he worked on PLL and clock synthesizers. Thereafter, he was with the Institute of Microelectronics, University of ULM, Germany from 2016 to 2018 as a group leader of Data Converter Group. He has also been a visiting professor at TU Munich, Germany in summer of 2022. He is a recipient of the Best Student Paper Award in IEEE International Symposium on Circuits and Systems 2013-2022 and Global Visiting Professor Award by TUM Germany and 2023 Outstanding Reviewer Award by IEEE SSCS. He is currently the Associate Editor of IEEE Transactions on Circuits and Systems too. He expresses his he is a member of the Analog Signal Processing Technical Committee of IEEE Circuit and Systems Society. His research interests are in the field of analog and mixed signal circuit design, focusing on the design of analog to digital converters and on-chip power management circuits. I would request Dr. Jain to please take over the stage and start with the session. Thanks.
Thank you very much for the kind introduction. So, how to go in full screen mode? Huh? Can we go in? Yeah. Is it downloaded? This one. Yeah. You just go here. Yeah.
No, sir, it's not yours.
Oh, this is not.
So is it yours?
Maybe. Yes.
Yeah.
All right. Thank you. So today I'm going to. Am I audible? Okay. So today I'm going to talk about self-powered sensor interface circuitry. So the outline of the talk is as follows. First, I will give a brief introduction of why do we need such kind of circuitries. I will talk about little bit prior arts. Then I will discuss hybrid energy harvesters. Then I will talk about a SCC technique, which is a technique to harvest the energy from these harvesters. I will discuss briefly nonlinear energy harvester, then the application of SCC technique to extract the energy from nonlinear energy harvesters, and finally I will conclude. So nowadays we see that everywhere we have a lot of sensor networks, and many times these sensor networks can also be in wireless mode. So now in such scenario, you need to have some source of energy to run these sensor circuitries, and this source of energy is mostly battery. So what you need is time to time you need to replace this battery, and which is not a very good technique because this becomes a costly affair, as you need somebody who should go there, who should replace the battery. So another alternative is to harvest the energy from the ambient environment. In our environment, the energy is present in several different ways. For example, we do have a lot of micro vibrations, which can be converted into electrical energy using transduction mechanisms such as piezoelectric mechanism, electromagnetic induction mechanism, and electrostatic mechanism are also there. So there are already several different kind of devices which can be used to harvest this energy from the environment. Now the challenge is the because the vibrations are very tiny, so the energy which is harvested is also very small. So now if you want to enhance this, then the idea is, can you deploy different transduction mechanisms together so that you can increase the overall output? And this brings us to the concept of hybrid energy harvesters. So at a device level, how do we do this? So for example, on the top right, we see the front view of two devices, which are energy harvester, piezoelectric based and electromagnetic based. And in the bottom figure, what we are doing is we are trying to incorporate these two mechanisms on a single device. So for example, we have a cantilever, and on a cantilever, we have placed a piezoelectric layer. And on bottom of it, we have also attached a permanent magnet, and on the below platform, we have a coil. So now whenever the vibration happens, the cantilever moves and it induces an electrical current in the piezoelectric layer due to strain. And also the movement of magnet induces some current in the coil, and thus we are getting the electrical current generated due to two different mechanisms. Now, the point is we got the electrical current, but now we need to take it to the battery. So if we want to take it to the battery, what is the challenge? The challenge is if we model these devices. So for example, piezoelectric devices are generally modeled as a current source in shunt with a capacitance. Is this capacitance is a small capacitance. So because of the output impedance, okay. So because of this, the output impedance is relatively higher. While in the case of electromagnetic energy harvesters, the output impedance is relatively low. So now, if you remember the basic circuit theory class, if you want to transfer the power in a maximum way, you have to follow the maximum power transfer rule, which says that the impedance has to be matched. Now, if we have a common load and we have two different output impedances, then it is very difficult to match the output impedance simultaneously in this case. So, what actually happens because of that, if we see this picture, because the two devices are coming in parallel, so obviously the lower output impedance will be the effective output impedance, and that's what we are seeing here. That the hybrid device is mostly following the lower output impedance profile, and when when the piezoelectric output is relatively high, even then the hybrid output is much lower because the output impedance of piezoelectric device is much higher. So how do we tackle this? The way of tackling is you cannot directly interface these devices with the load. You have to bring something in between so that these impedance can be matched, and then you can extract the energy in a more efficient way. So how do people generally do it? For example, in case of electromagnetic energy harvester, where the output impedance is generally low, if you want to increase it, the one way of doing this is you enhance the output voltage. Because if you enhance the output voltage, effectively the impedance is increasing. So you use either charge pump to boost this output, or you also use some boost converter, which is a an efficient way to enhance this voltage output. Now another challenge with this output is because these are vibrations which are varying in nature. So the electric current which gets generated is also varying in nature, or let's say electrical voltage which gets generated is varying in nature. But if you remember, most of the time battery output voltage we need constant. So the second thing you need to do is do some rectification. So rectification circuitry is very conventional circuitry. We can use a bridge rectifier to convert this AC generated voltage into a DC output voltage, and that can be stored on a capacitor or a battery. Now, in case of piezoelectric energy harvester, because the output impedance is already high, so we need not to enhance the output voltage. In this case, you can directly use the rectification and we can get the rectified output. Now, in case of rectified output, if our output voltage is very low, then we see that for most of the time, the source is connected to the load. However, because the output voltage is low, so the energy output is also low because energy output is nothing but the voltage into current. On the other hand, if the output voltage is high, then in that case, the rectifier is on for very small duration. So in this case, although the output voltage is high, but because current is getting passed only for a certain duration, so the energy output is again low. So only for somewhere in between the energy output is relatively higher because in that case you can say both the voltage and currents are relatively decent and then we get a decent output. So this technique generally requires the proper tracking of the operating voltage or the output voltage and is known as maximum power point tracking, which is commonly used in this circuitry in order to get an efficient output. Now, sometimes the diode drop can become a problem, especially if your input voltage is low. So in such case, you use techniques like NVC and active diode based solution, which can give you very small drop. So these are like conventional techniques which actually can be used. As we have seen in case of these techniques, it requires the output voltage to be tracked like using MPPT. So there is another interesting technique which doesn't require this. And this technique has a very simple phenomena. So think about this like For example, if we have piezoelectric output stored on a capacitor, which is a parasitic capacitor, and if we want to extract this energy, then one thing which we can do is you can just bring one external inductor L as shown in this figure on the right hand side, and then try to resonate this capacitor with the inductor. Now, as we know, if LC resonance happens, then after certain duration, the whole energy from the capacitor will get transferred to the inductor. And as soon as this happens, you can break the connection. And now, because all the energy is with the inductor, what you can do is now you can again resonate this inductor with an external capacitor CS. So now the energy from the inductor can again be transferred to the CS. And if you keep on repeating this, you can actually transfer the complete energy from CP to CS using two resonance cycles. And this is a very interesting technique because it's a sort of lossless mechanism because LC resonance is a lossless mechanism and only switch resistance will be a loss which if realized very small can be a very efficient technique. Another interesting aspect of this technique is the CP can have any value. So basically it is independent of the load. So only timing has to be adjusted so that we can figure out when the energy gets completely transferred to the end. So we found this technique very interesting. And in fact, there are certain prior work which already uses this technique for extracting the energy from the multiple sources as shown in this figure. In this case, they were kind of time sharing this inductor with the multiple sources. So the energy from different capacitors are getting transferred one by one to the inductor. And then finally, this energy is getting transferred to the load. What we wanted to do is because in this case although the time sharing was happening, so not simultaneously the energy was getting transferred while we wanted to transfer the energy simultaneously. So we thought this problem in a very simplistic way. The basic of this energy transfer is the LC resonance. So if C is my source, what I want to do is I want to do a LC resonance and I want to transfer this energy completely to the L by doing a resonance. So I can also think this capacitor as a series combination of two different capacitors. And now in this series combination, the middle point can even be connected to a ground voltage that doesn't change much. And then what I can do is I can split these two capacitors in this way. And now I can treat them as two independent sources. And the whole LC resonance concept is still valid because you have a C and you have a L. But what you are doing now is now you can transfer the energy from the two sources simultaneously to the inductor. The point at which the energy get transferred is the point when the voltage across the inductor is zero. Because at that point, the current through the inductor is maximum, which means the energy through it is maximum. And using the same idea, we took the conventional approach and we noticed that in the conventional approach, the other end of the inductor is basically connected to the ground. So what we did is instead of remaining it connected to the ground, we connected it to the second source as shown in the blue color wiring. So now by doing this, we could transfer the energy from these two sources simultaneously, and this has helped us in extracting the energy in an efficient way. So this is like earlier, whatever I have told, that was the original intention. But sometimes what happens is whenever you try something, something can happen which even you have not expected. And this in this picture, I want to highlight the thing which we have not expected, but which we got as an additional benefit of this technique. So the idea was in this, as I mentioned you earlier, the voltage across L becomes zero as soon as the energy through the inductor is maximum. Now at this point, suppose the other capacitor, let's say if it has certain negative voltage, that means the first capacitor will also get a negative voltage at this point. And now if my next cycle of the AC cycle is essentially the negative portion of the AC cycle, then what I am doing is I am starting from a negative voltage and I am further going into more negative. So this is like you are starting from a point which is already energy investment, and then you are going to a higher negative voltage. And this is a popular technique which is known as energy investment in the context of energy harvesters. And this we are kind of getting for free here. So by doing this, this is the final output. And from this, we can effectively see in the hybrid case, we are actually combining the two individual output, and then our energy is more efficient. Now, although we have got effective benefit from this approach, but most of the time when we use piezoelectric harvesters, this particular or in many cases what we do is we use a very narrow linear kind of energy harvesters. So these linear energy harvesters operate in a very narrow frequency range, because of which the energy output from a narrow frequency range can only be harvested. There exists another variety of energy harvester which are known as nonlinear energy harvester, which can operate in a much wider frequency range. The problem with these energy harvester is that they do have two different energy states. So if you are lucky and if you get to go into the high energy state, then your energy output will be much higher. But randomly you can also land up in the low energy state. And if you land up in low energy state, then the energy output will be much lower. So now the how do we ensure that we end up in high energy state? It is quite random, but there is one process. The process is known as energy injection. If you somehow manage to do some energy injection during the operation of energy harvester, then you can ensure that you end up in high energy state. But this is counterintuitive because we want to harvest the energy. And for doing that, if we have to inject the energy, that means we need to have an energy source, and this becomes a problem. So in order to solve this problem, we actually used our previous idea where we were saying that we are trying to harvest the energy from two sources simultaneously. Now we picked up this problem slightly differently. We say that one of the source is the nonlinear source, and the other source I will use to inject the energy on the nonlinear source whenever it go in low energy state. So by doing this, we could actually ensure that I will directly show you the result. Yeah, these are the results. So here we can see that whenever we are injecting the energy output is effectively going to a much higher value. And in fact, let me show you the simulation results. So this is one of the result where we can see if our device is in low energy state, then your energy output is almost negligible. But using the proposed technique, we could ensure that it always lands up in high energy state, and we can see the energy output was much significant. So finally, to conclude, we can say that using this technique, we have demonstrated efficient circuits for hybrid energy harvesting. The SCCE technique, which is synchronous electric charge extraction, is load independent and allows efficient extraction of energy from multiple sources. Energy injection allows the use of nonlinear energy harvesters. An order of 80x improvement is possible with this particular techniques over conventional approaches. Very recently, we have got this chip back and we have done some measurement results. And in fact, the measurement results are confirming whatever we have noticed during the simulation, and we are very soon going to publish this work. Thank you.
Thank you, sir, for such a fascinating talk. I would request if participants have any queries. There are no queries. So I would like to.
So right now our energy output is in the range of 100 to 200 microwatts. This is for 1 centimeter square kind of device. So obviously, if you increase the area, then energy output will be higher. But right now we are in the range of 100 to 200 microwatts. Yeah.
Yeah, thank you.
Okay.
Typically, like for nano generator, voltage pass is very high. Current pulse also is not less. So can we also capture those pulses, like not continuous source, but it's like pulse,
Yeah.
very high voltage pulse.
So you are talking about triboelectric energy harvester. So we have worked on that also. So there are two ways of handling it. So one way is you can intentionally put some additional capacitance at the output of this energy harvester. So basically, what you are doing is you are storing that charge which is coming instantaneously, and you are now pulse shaping it so that the output which goes further becomes more smoother and you can handle it. That is one approach. Another approach is like there are certain process which allows you even on chip to handle much higher voltage. For example, there are CMOS process which can cater up to like 80 to 100 volt devices. So you go for such sophisticated process, and there also you can handle. But again, it depends because there are triboelectric energy harvester which can go up to let's say 500 volt or also. So basically the way is same. Like if the moment it is going beyond your range, you put some additional capacitor, bring it back to your normal range, and then you do that.
Now, I would like to invite Professor Deepak Goswami sir to present a memento to Dr. Jain as a token of appreciation and gratitude. Thank you, Dr. Jain, for taking out time to share your expertise with our IEEE community. Moving next, we have our next invited talk from Professor Bimal Bhatia, sir, professor here in the Department of Electrical Engineering at IIT Indore. Professor Bhatia is currently working as a professor HAG with the Indian Institute of Technology Indore, India, and is an HM faculty at IIT Delhi and IIIT Delhi, India. He received PhD degree from Institute for Digital Communications with the University of Edinburgh, Edinburgh, UK in 2006. During PhD, he also received the IEEE Fellowship for Collaborative Research at the Department of Systems and Computer Engineering, Carleton University, Canada, and is Young Faculty Research Fellow from MIT Government of India. He is also a recipient of Professor S. N. Mitra Memorial Award 2024, Professor SPCIA Memorial Award 2019, National Slovak Fellowship and European Mobility Scheme as Senior Researcher at Czech Republic. He has worked with various IT companies for over 11 years both in India and UK. He is a PI PI coordinator for external projects with funding of over USD 35 million from MIT, DST, Ukraine, MOE, EKA, IUSSTF, and KPMG. He has more than 480 peer-reviewed publications and has filed 17 patents, out of which 13 are granted. He has supervised 26 awarded PhDs and 2 PhD theses submitted. His research interests are in the broader areas of communication, non-Gaussian, non-parametric signal processing, machine or deep learning with applications to communications and photonics. He is the reviewer for IEEE, Elsewhere, BB, Springer, and IET. He is currently senior member of IEEE Fellow IETE and Certified Scrum Master. He was also the General Co-Chair for IEEE ANTS 2018 and General Vice Chair for IEEE ANTS 2017. He has delivered many talks, tutorials, and conducted faculty development programs for the World Bank's NPIU TEQIP3 invited talk at WWW RF46 Paris and others. He is currently Associate Editor for IET Technical Review, Frontiers in Communications and Networks, Frontier in Signal Processing, IEEE Transactions on Green Communications and Networking, and IEEE Wireless Communications Letter. He is currently member steering committee for IEEE NTS. He has been mentioned among the world's top 2% scientists by the Stanford University since 2021. I would now request Professor Bhatia to please take over the session and continue with
अच्छा अच्छा वही है क्या हम मौसी का Good afternoon. Thank you so much for the technical introduction. I think it was about half an hour, 20 minutes. Okay. Okay, so yeah, slides that more. So I'll try to squeeze some parts. So I saw that in the schedule that there are talks from many different people in different areas. So I had some initial slides on wireless communication that I might even skip and then move on to the actual topic. And it is interesting that the previous talk was also on energy harvesting and looking at energy efficient ways, which is useful for us as a communication engineers because as we move towards 6G and beyond, we're looking at IoT and the expectation of a device in 5G expectation was for 10 years of battery life. Now 6G we're talking about 20 years of battery life. So if we have energy harvesters which can harvest RF energy or some other ways, make RF from somewhere else, which can have these device IoT of devices to be active for the 30 years, for the KPI. So just quickly notice a few things which are quite generic if you done a course on communication. But just an overview that yeah, wireless communication is something which is very important. Each one of us has at least one phone, sometimes we have two phones as well. Plus we have a laptop, we might use Bluetooth. So wireless communication is everywhere. Uh, so as to why it matters, because we want to have uninterrupted access, high data demand, reliability is important. Maximizing the throughput through different applications and next generation. So we are now using mostly 5G, moving towards 6G by 2030, and then we go towards 7G and beyond. Just a brief overview of communication, transmitter, and receiver. This is what we can skip on interest of time. Yeah, basically, but this is important. So here, when you look at a wireless communication channel, channel impairments, they play a very important role. We have a major contributor to that is a path loss. So path loss is inversely proportional to the distance that we are transmitting the signal to, and also to the frequency as well. So the higher the frequency, the more losses we have in the free space. So in communication system, we are moving upwards of the frequency range. We are moving from to 100 megahertz to gigahertz, and now looking at terahertz from 60 onwards. So that is obviously going to reduce the distance that is traveled by the signal. So there's a lot of drop that happens. Then of course there are other factors like the multipath fading and the device connection, they impact the performance. So basically the performance of the system depends is affected by attenuation, noise, fading, interference, mobility, and bandwidth effects. And these are some of the metrics which again will not go into details in interest of time. Skip this part. Uh, so things like outage count, this is an important measure which checks if the received SNR is below a certain, if it's below a certain threshold, then we cannot communicate. So we always try to have it more. So our objective in any communication system is to keep the receive powers higher than the threshold, so that the communication can flow ahead. Um, and of course, the original capacity is also dependent on SNR. So SNR is another thing. But again, we cannot infinitely keep on increasing the signal power. Again, that's limited by the regulators. We can't really go so much far. Same thing with the bandwidth as well. So there are now certain newer developments that has happened over the past few years, where we can try to improve the or reduce the path loss by certain different techniques. And then again, MIMO in parallel was a big development where we can promote with the antennas and both transmitter and the same more than one. And we can have different combination of these. We can have a higher number of antennas of the transmitter or the base station and lower as our handset because again power constraints are there and the size also they mixing. This is a brief overview that you can have a SISO, which is very common when we initially start working on. Then we have MISO, SIMO, and a full MIMO that we can do. So our focus in a communication system is to increase the transmission uh, power, or we want to reduce the usage of power, so at least we get the similar performance. So for that, in recent works, it has come out that we can use antenna structure, which is like which we call it as a fluid antenna system, which is different than what we are currently using in our handsets. So the advantage is there's no fixed position, so we can uh, change the position which are what we call ports in flexible or fluid antenna system. So we can change the position of the dynamically change the position of the port that needs to be activated so that we get the maximum energy that we're receiving at the receiver. So the current implementations are where we have our antennas that are fixed, limited special degrees of freedom out there because we can't really change them to the higher cost and higher complexity. Inefficient diversity utilization because once it is fixed, you can't really change it much. High complexity again correlation reduced degradation and with architecture. So we're moving forward looking at fluid antenna systems where you can have, let's say you have a mobile phone, either on the periphery or on the screen itself. You can have some material where you can have different ports, and they can be activated where the we want to, let's say, getting the maximum power, the maximum energy we're receiving at the receiver. So the idea is that instead of using all of those, we activate only the ones where the maximum energy can be received. So this gives us a lot of advantages that it reduces the hardware, energy, and the space requirement. It enhances reliability, data rates, real-time response because we're changing the position, which is supporting the 6G performance that we get. And it can be applied in various places. It doesn't need to be only at the user equipment or the handsets. It can be in other places as well. That we'll see there are a few figures that show the system diagrams. Uh, and with only one RF chain, because RF chain is expensive to be put both computationally, cost-wise, space-wise as well. So you can use one RF chain only and activate the ports which are of interest. And finds dynamically reconfigures the shape and position with limited space so that we get the maximum signal quality and does it or performs the traditional one. So this is one type of system diagram. So that shows that you have a handset and you might have these small ports here that get activated. The signal will come from maybe bounce from the walls, it can be directed as well. But we activate the antenna, which where we are getting the maximum power. Now, this initial designs for that we have a fluid which can be pumped through a micro pump, which can go through different parts or just on the periphery as well. Maybe good enough. So we have a small liquid that can go around and it captures the energy or stays where the highest energy is going to be there. But now the definition of fluid is a little bit different. It may not be a liquid, but it could be anything which is changes. So used as a verb. Yeah, so I'll skip this part. So there's a one system model that we played with. So we have a source, we have various relays networks, and then at the user we have a multiple of these fluid antennas stored. Let's skip these results as well. Now there's another topology where these can we also use in risk formation. So we call this FIRES, where it's not the UE, it is fluid antenna at the risk it is stored. So again, similar principle, we can activate the ones where we are which we are interested in. It also in a way supports multi-user better than the risk. It's more flexibility in the system. And then, yeah, we'll skip some of the results. And then it can also be used in the base station. So we can also have, yes, this one here. So we can also have risk in the base station where we have this antenna and we can divide it into four different regions. We can have multiple users being served. So it's not that the full BRIS panel will be used for only one user. So now there's more configurability. We can use. So this basically shows that we can use fluid integrated systems on for the UE, for the RIS, and also for the base station. So all the three largely components of communication system. So moving forward, I mean, this was okay. I'll say till now, still a lot of research is going on, but still it has some limitations, and there are a lot of other areas that people can look into for future communication systems. But what we looked at, that there are other things like MIMO advantages, looking at Roma into Frizz. Yeah, they can be put into fluid integrated systems as well. But then there is another issue is that risk or they came because of the ability to have a line of sight. So basically, it improves the coverage where signal is not there. But drawbacks are suffers from double attenuation because it goes to the risk first and then from risk the signal goes to